Welcome to Hartman Math. This is lesson 7.6, linear programming, which is a branch of mathematics all on its own. So this is just going to be an introduction. Back in the previous lesson, we looked at solving and graphing a system of inequalities. And that would be based, in this case, on, those would be constraints. And that would generate our feasible solutions. And so the optimal solution is going to have to occur at somewhere in here, and it's usually going to be at one of the edges, one of the vertices. So what we're going to do is use those constraints, sketch the region corresponding to the system of constraints, the inequalities, find the vertices, and evaluate. There's going to be some sort of an objective function, so we're going to evaluate that function at each of the vertices and see what's our best situation. So example number 1, our objective function is here, z equals 2x plus 8y, and here are the constraints. So we've got x is greater than or equal to 0, and y is greater than or equal to 0, and then this last one here, we could do, you could get y by itself, but maybe easiest just to get it in terms of finding the intercepts. So substituting 0 for y, you get an x-intercept of 2, and then the y-intercept of 4. And we can draw the line, it's going to be solid, and if we test something like the origin, 0 is less than or equal to 4, it's going to be true. We're going to shade here. So if we shade in our feasible solutions here, the solution to the system of inequalities, we are right here. So our vertices, doesn't really matter, I like to kind of go in counterclockwise order, but we got vertices here, here, and here. So our vertices are the origin, in which case if we substitute in 0 for x and 0 for y into our objective function, we get 0. We got 2 comma 0, leading to a value of z for our objective function of 4, and 0 comma 4, where we're going to get 0 plus 32 is 32. So the minimum is this, it occurs here. The maximum is 32, it occurs here. So we're not really sure, are we looking to minimize the function, maximize the function? So we'll list both. The minimum is 0, it occurs at 0, 0. The maximum is 32, and it occurs at 0 comma 4. Example number 2. Here are our constraints. Our scale is going to go by 2. So again, it's going to be very common because this is going to really have real-world applications, whether we're producing product or something like that. And things in that case usually can't be negative. So these are going to be very common constraints. Again, so just the first 2 means that we're going to be dealing with quadrant number 1. And then on the axes at that point. So if we do, again, finding intercepts, we're going to get x-intercept of 10 comma 0, y-intercept of 0 comma 4. That's going to be shade inside. And then for the second one, an x-intercept of 8, 2, 4, 6, 8. And a y-intercept of 2. Notice that the sign is flipped on that one, so if we test the origin, it's not going to be true. We're going to shade above on that one. So our vertices are here, 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 and here. So we have a vertex at 8 comma 0. If we substitute that in, we're going to get 16. We've got 10 comma 0, 20. We've got 0 comma 4. 28, and we've got 0 comma 2, 14. So we have a minimum of 14 that occurs at 0 comma 2, maximum of 28 that occurs at 0 comma 4. Example number 5, we want to optimize profit here, and a manufacturer wants to maximize the profit producing 2 different products. Product 1, which yields a profit of $1.50 per unit, and product 2, yields a profit of $2 per unit. How many of each type should be made to maximize the profit? Under the following constraints. The production level should not exceed 12,000 units total. Demand for product 2 is no more than half the demand for product 1. And the production level of product 1 is less than or equal to 600 units plus 3 times the production level of product 2. So we need to use the constraints to generate our system of inequalities. So if we say X is the number of product 1 that we're going to produce, and maybe Y is the number of product 2 that we're going to produce, then we would start out here, production level should not exceed 1,200 units. X plus Y would have to be less than or equal to 1,200. So here's our let statement, X and Y. What about that second constraint? Demand for product 2 is no more than half the demand for product 1. No more than half, less than or equal to half. So Y less than or equal to 1/2 X. And the last one, X is less than or equal to 3Y plus 600. The ones I did not write down, I probably should, is X has to be greater than or equal to 0. Y has to be greater than or equal to 0. Kind of assumed in this case, I'm talking about making product. Obviously can't make negative 100 units of something. So here's our graph. We're going by 200s here. So first one here, we can go by intercepts. Intercept 1,200 and 1,200. Use the slope here, so up 200, right 400. Okay, so we're going to shade below there. We're going to shade below on that one. The tricky one here, we're not used to equations like that. We may want to solve for y, get this into kind of a y equals mx plus b situation. If we do so, it looks like that. So negative 200 for the y-intercept, slope of 1/3, so up 200, right 600. And in that case, that would be shade above. And remember, we are still using the axes here, so we're going to shade above the x-axis. So our vertices here, 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 and here. Now the one that's a little bit tricky here is this one here. Did not occur at a grid point. So we're going to have to algebraically figure out those values for the vertices there. So we have to figure out which two lines we're intersecting to create that. And it was the last one that we did, so I might do it based off of this and the first one. So maybe we could do a substitution. We're assuming at this point on the boundary lines being equals and equals. So we can replace x with 3y plus 600. 3y plus 600 plus another y is 1,200. So 4y plus 600 equals 1,200. Subtract 600 both sides. 4y equals 600. Y has to be 150. And then when we plug that back in, I think we're going to find x is 1,050. So algebraically find it when the graph doesn't reveal. 0, 0. 600, that's going to produce a profit of 900. And the one that we were just talking about, substitute for x and y, get 1,875. And then this one here looks like we're at 800, 400. And there we go. We are trying to maximize profit, so we don't even need to look at the minimum. We're right here. We can have a profit of 2,000 when we produce 800 of product 1, 400 of product 2. Example 5, plus furniture manufacturer makes 2 types of coffee tables, circular, which requires in the shop 3 hours of skilled labor and 6 hours of unskilled labor, and produces a profit of $50. A rectangular table requires 2 hours of each of the types of labor and yields a profit of 30. 90 hours of skilled labor are available, 120 hours of unskilled labor are available. those are the constraints. Those are the limitations. So we've got an inequality for the 90 hours and another inequality for the 120 hours. So let's say X is the number of circular tables that we're going to make, and Y is going to be the number of rectangular. Okay, so first of all, our profit function, that one's pretty easy. Okay, 50 and 30, so our profit function, P is equal to 50 times X plus 30 times Y. And then our constraints, we kind of go back and take a look at that. Again, we've got a constraint for 90 and a constraint for 120. So the skilled constraint is, well, if it takes 3 hours of skilled for a circular table, 3 times X, and 2 of each, so 2 for skilled here, 2 times Y, that has to be less than or equal to the 90. And if we do the unskilled constraint, 6 hours of unskilled per circular table, so 6X, and another 2Y is going to be less than or equal to the 120. And then again, X has to be greater than or equal to 0, Y has to be greater than or equal to 0. Let's graph this, each of these based off of tens. So here we've got an x-intercept of 30, 0, y-intercept of 0, 45, and x-intercept of 20, and a y-intercept of 60. So there we go. If we also put in the x is greater than or equal to 0, y is greater than or equal to 0, here are our vertices. It's like all of these fairly easy to see. Definitely not going up here. That's not in the shaded region. We are here. So our vertices 0, 0, 20, 0. We can make just 20 circular tables. We've got 10, 30. Profit's 1,400. And we've got 0, 45. The profit's 1,350. So here's our best situation. If you were a consultant on this project, they said, what should we do? This is what you're going to recommend. 10 circular tables and 30 rectangular tables. All right, we're going to look at one more. Example 6, where we might see a vertex that's actually not at integers, and then we might see a solution that's not at a vertex. Our Carl's Carpentry Company makes 2 models of cabinets, basic and presidential. Basic cabinet requires 2 hours of construction, 1 hour of finishing, and it makes a profit of $90. A presidential, 5 hours of construction, 2 hours of finishing, and produces a profit of $250. Carl's Carpentry Corp has 80 hours of construction and 36 hours of finishing available to it. How many of each should be produced to maximize profits? Let's say X is the number of basic cabinets made, and Y is the number of presidential. Again, profit function should be pretty easy. Profit is going to equal 90 times X plus 250 times Y. And we got to get into our constraints. We're going to have a constraint for construction and one for finishing. So for construction, on the basic, 2x plus, again, construction, 5 of the presidential. So 5y has to be less than or equal to the 84. And then our finishing, 1 hour of finishing, so 1x, 2 hours of finishing plus 2y has to be less than or equal to 36. All right, let's graph. These are based off of 5s. Or should I say 8s? Let's try it that way. Scale by 8s. So if we find intercepts, we're going to get 42 for x, just a little bit past there. And so here's really the issue. We're going to get a vertex at 16.8, or at least a y-intercept there at 16.8. We'll see if it's a vertex there. So 16.8 there, just a little bit higher than 16, and then 36 and 18. So an unknown vertex there. So we'll need to go ahead and find that. So maybe if we multiplied this one by -2 and added, you can eliminate the x's. So we get 1y is equal to 84 minus 72, so 12. So y would be 12 right there. So y is 12. I think that's going to make x 12 as well. But again, here is this issue, because right there, which is the y-intercept here, it's 16.8. And if we're talking about the number of presidential cabinets, we can't go deliver to someone 0.8 of a cabinet. When it shows up, they're going to go, that's not a whole cabinet. What am I supposed to do with this? So we can't make 16.8. We've got 0, 0. We've got 36, 0. We've got 12, 12. And then over here, since we can't make 16.8, the next best is 16. We can't go up. We don't have enough resources to make 17. We can make 16. It falls within there. So we can do that. So you might think this is our best option. I don't know, maybe. Here's the thing. Since we didn't go all the way up to the 16.8 and we came back down to 16, there are some unused resources. So let's look at that, because we dropped down here. So really looking at this one. If we only made 16 of the y's, so what's 5 times 16 as far as a resource there? That's 80. That means we still could make a few more x's in this case instead of making 0 x's and 16 y's. This constraint says, well, if that's 80, x could be 2. That could be 2 comma 16. In which case, that's our best option right there. A little bit tricky. But there we go. We're going to make 2 basics and 16 presidentials, and that's our best option. And that's it for today. I'll see you next time.